new stuff. The first one is the concept of rotational kinetic energy. So I should just stop saying the names of things first? Sorry, this is something new. We have kinetic energy. So, if we talk about an object with shape, and it's rotating, it has different pieces that are rotating at different angular velocities, or different linear velocities. All the angular velocities are going to be the same. And so we're going to actually have kinetic energy associated with all the pieces of the object. So the total kinetic energy of the object is going to be the sum of the kinetic energies of each individual piece. Now, what this I means is we're taking the, talking about the kinetic energy of each individual piece. So that I goes from 0 to approximately infinity. Because we're going to take this piece and we're going to break it into eventually an infinitely small number, or infinitely large number of infinitesimally small pieces. Again. So we know the total then is going to be equal to the integral of, I'm sorry, not the integral, but the sum of, I'll make that a little more clear. The sum from I to however many we have.
Is that a sum or is that negative?
That's a sum, sigma. 1/2 MIVI squared. Again, because what we're talking about is we're talking about the mass of these pieces and the velocity of each one of these pieces. We've actually just talked about the velocity of each one of these pieces. It's actually equal to r times omega. So this is going to be equal to, again, the sum of all of the pieces, 1/2 mass times r, the radius of each piece from the axis of rotation, times the angular velocity of each piece, squared. Now, we know, and I'll do this, so 1/2 MIRI squared omega squared. We know that the angular velocity of each one of these pieces is going to be the same. So what I'm going to talk about here is the kinetic energy total is equal to 1/2 times the sum of the mass times the distance from the axis of rotation squared. So this r is the distance from the axis of rotation. And this has a specific name. I is equal to the sum of the mass times the distance from the axis of rotation squared, where I, unfortunately, does not stand for impulse. I stands for the moment of inertia. Now, I find that the moment of inertia is not a very descriptive term for, or not a very helpful term, I guess, for what this represents. And so what I often will call this is, it is rotational mass. In order to understand what I mean by rotational mass, please remind me, what is mass? What is mass? Who could tell? Don't worry, it goes back to chapter 2 or something. No, actually, it's actually chapter 4, I'm sorry, of college prep physics. Nick?
Measure of inertia.
Great, it's a measure of inertia, so we need to define inertia. What is inertia? Silva?
How difficult it is to move, change something.
The resistance to an acceleration, the tendency of an object to resist a change in state of motion, or a resistance to an acceleration. So mass is literally a measure of how much resistance an object has to acceleration. Rotational mass is how much resistance something has to an angular acceleration. So the moment of inertia is its resistance to, it's a measure of the resistance of how much resistance it has to the angular acceleration. And so notice that it's where the mass is located relative to the axis of rotation. So the farther the mass is from the axis of rotation, the larger the rotational mass, the larger the resistance to a change in state of angular motion, or a resistance to angular acceleration. So what I have here is a small demonstration piece, which is I'm going to hand around so everyone can feel the difference. Now, if I have the two masses in the middle and I rotate it, there's a certain amount of inertia, moment of inertia, or resistance to this angular acceleration. And if I take this mass and I move it out farther away from the axis of rotation, what do I do to the rotational mass, Vlad? I increase it. So with these masses farther away from the middle, the axis of rotation, it makes it more difficult for me to cause an angular acceleration to this object. So what I want you to do is hand this around and take a moment and do this, move it to the middle, and feel the difference between spinning it with the masses in the middle, where this is very easy because the moment of inertia is small, whereas this is much harder because the moment of inertia, rotational mass, or the measurement of the resistance to an angular acceleration is increased. So please, take a turn, hand it to the next person. Don't hurt anyone. So it is where the mass is located relative to the axis of rotation. Let's walk through just a simple example involving two objects here so we can figure out how this works.
Should we finish our equation first, or?
We have.
Like, can you just put the I?
Oh, sure, here you go. Okay, sorry. The kinetic energy total, rotational kinetic energy, is equal to 1/2 I omega squared. This is rotational kinetic energy. Note how similar it is to linear kinetic energy, right? 1/2 mass times velocity squared. You can see that I, the moment of inertia, even takes the spot of the mass in 1/2 mv squared, and the angular velocity takes the location of the velocity. Mohit, you still have a question? Okay. So, in our example, it's going to look surprisingly like the demonstration model that you have going around. We're going to have a thin rod, which is going to be connecting two masses. That was not very good, but that's fine. Thin rod. Now, the term thin is something you need to be able to identify. The thin rod means that this rod has zero mass and zero thickness, zero everything, pretty much. It is an object that is connecting the two masses, but it has no mass itself. It is essentially negligible. So this is a term that you need to become familiar with, the concept of a thin rod. So each object has a mass of 2.0 kilograms. And we're going to spin this object about the middle, about the axis of rotation, at an angular speed of 1.5 revolutions per minute, or 1.5 RPMs. We're going to figure out two things. We're going to start out by figuring out the moment of inertia of this, which is just going to be the sum of the masses and the distance from the axis of rotation. So what is the moment of inertia equal to for this particular object? What are the numbers here? Tyler.
Wait.
That's fine.
All right, what?
Trying to figure out the moment of inertia of this object, which is rotating about its axis of rotation, which is right at the center of mass of the object.
All right, it's going to be 2 times 1.5 squared, except there's two masses, so...
Oh, I didn't give you a piece of information which is going to be important here. No, let me just, hold up, 1 second. I'm going to pretend that we said this, which is that the length of the whole thing is equal to 1.0 meters. That's going to be helpful. Just throwing it out there. You're going to need that.
So it's going to be 2 times 1 squared, but I think it would be 4 instead of 2 because there's two masses of 2.
Okay, that's okay. You're not understanding it. That's fine. Let's do it this way. And we're going to do it with letters just to make sure. We'll call this one mass 1 and this one mass 2. So this is going to be mass 1 times R1 squared plus mass 2 times R2 squared, because this is the sigma, or the sum of these. So help them out here, Vlad. What's mass 1?
2 kilograms.
What is R1?
0.5 meters.
0.5 meters. That's the distance from the axis of rotation. So That's what r is. So the distance over axis of rotation 0.5, which we're going to square, plus, and then it's redundant. The other one is the same thing, 2 times 0.5 squared. So the moment of inertia around the center of mass for this object is what? 1. We can do 1.0. And what are the dimensions? Nitish.
Kilograms times meters squared.
The dimensions for moment of inertia are kilograms times meters squared. Those are the dimensions for the moment of inertia. So now we can figure out the rotational kinetic energy, which is going to be 1/2 I times omega squared. Help me figure out the rotational kinetic energy here. Message.
1/2 times 1 times 1.5. Or actually, I guess if you convert revolutions per minute
To what?
to the radians per second.
We need to convert revolutions per minute to radians per second. So 1.5 revolutions per minute. Please convert 1.5 revolutions per minute to radians per second. Padarella.
All right, so you already wrote it out, very nice. On the bottom, you have 1 revolution is equal to 2 pi radians. Or, sorry, on the top is 2 pi radians. And then in parentheses, and then you have on the, those cancel out. On the denominator, you have 60 seconds. In the numerator, you have 1 minute.
Minute cancels out. We're now in radians per second. Can I please have the number here? That's in radians per second. So we have 0.157079 squared. We get
1, 2, 3, 3, 6.
1, 2, 3, 3, 6.
Yeah.
This is equal to then 12.3 what?
Or
12.3 De Silva?
kilogram meters cubed per second.
We're close. I'm not going to disagree with that, but that's not quite what we have here. Jenkins?
Per second.
No. Travis?
Millijoules?
It'll be in millijoules.
Oh, millijoules.
I converted over just for fun. We have it in millijoules. Now, show me that this works out to be joules. Emily?
Well,
1/2. The dimensions on moment of inertia.
It would be kilograms times meters per second, or meters squared.
Meters squared multiplied by angular velocity.
Meters per second.
Angular velocity. Not in meters per second.
Radians per second.
Radians per second. That's squared. So what we have here is kilograms times meters squared times radians squared divided by seconds squared. But Emily, you haven't told me how that is joules.
Oh, because your kilograms times meters per second.
How is that joules? No, it's not magic, it's physics. What's up?
Well, the radians aren't really units.
Remember, that's why we use radians, because the radians are dimensionless, so that can just go away.
Oh.
True. What else? But I'm still not at joules here. Nick?
Kilogram times meters per second squared is big.
Hold up. So kilograms times meters per second squared, we're left with meters, right? And a kilogram times meter per second squared is a Newton. Newton times a meter class is? Joule. So yeah, it works out to joule. That was for two particles. But what if instead we have an object with shape that we want to figure out the moment of inertia of? Well, that would be equal to the limit of the sum of Ri squared delta Mi as delta M goes to 0. That should look familiar. That is what? An integral. So the moment of inertia is equal to the integral of R squared dm. Basically what we're doing is we're taking an object, we're splitting it into an infinite number of infinitesimally small pieces, dm. Now, please be very careful now that I've introduced this equation for the moment of inertia of an object, a rigid object with shape. People often confuse this one with the x center of mass, which is 1 over the mass total integral of x dm. Note the similarity between the two. They are clearly very different equations, but they are often confused which one has the square, which one has the total mass, etc. So just be careful of those two.